Okay, so we have one more reaction to talk about, and then all of them together with regio and stereoselectivity and problems, and that's what we'll do today, and that's what we'll do tomorrow as well. So let's start with anti-Markovnikov addition of HBr. So we know, or hopefully we know, or will know in the near future, HBr plus an alkene is Markovnikov. The H goes to the carbon with the most hydrogens, and the bromine goes to the most substituted or the other one. So if I just add HBr to a double bond, I'm going to get Markovnikov addition, but if I want to switch that, I'm going to use hydrogen peroxide or an organic peroxide, which would have an ROOR. Hydrogen peroxide is HOOH. So the addition of those two compounds will change this reaction from Markovnikov to anti-Markovnikov, which basically means that we have a brand new mechanism. Is it a mechanism we have to know? Yes. And elements of this mechanism will be in free radical halogenation that we'll talk about when we get back. So let's take our double bond that we've been doing every reaction with, and let's add HBr and hydrogen peroxide to that. Okay. So for HBr and peroxide, what am I adding? HBr. How am I adding it? I'm adding it anti-Markovnikov, so that now the Br adds to the carbon with the most hydrogens and the H adds to the most substituted. So if I'm writing the product, that's going to be the major product of the reaction. Notice I haven't gotten to stereochemistry yet. I'm just dealing with, is it Markovnikov or anti-Markovnikov? So that would be this would be the major product of the reaction. It's not the exclusive product, but it's the major one. So we have a change in mechanism. And in order for us to talk about the mechanism, we're going to have to talk about radicals and what those are involved and what's involved with those. So let's start with the mechanism of this reaction. It starts with what's called an initiation step. And the initiation step is when the hydrogen peroxide splits apart to form two hydroxide, what are called radicals, or hydroxyl radicals. I'm going to write them like this. Okay. So when a molecule like containing oxygen or carbon has an unpaired electron, it's called a radical. Okay. Now, how did I break the OO bond to get that? We've been breaking bonds heterolytically, meaning that we've been breaking the bonds to give the more electronegative element the pair. But these two oxygens have the same electronegativity, so there's no reason why one should get both and the other one get none. So they're going to split evenly to give each one of the oxygens back its electron. Now the arrows that we use to show that are going to be what are called fishhooks. They're half arrows. A full-blown arrow that we've been drawing is the movement of two electrons. A fishhook arrow is one. Okay, so all the mechanisms that we do with free radicals involve one electron movements, and so they're going to be fishhook arrows. So we break the oxygen-oxygen bond and give each oxygen an unpaired electron. Now, those oxygens are not stable because they only have 7 electrons versus having 8. So they're going to want to get something with another unpaired electron to take them back to having a full octet. And in general, what radicals do is they abstract hydrogens. And that term is abstract hydrogen atoms. And so we'll see the example of that in the next step. So when I form a hydroxyl radical, that hydroxyl radical is going to react with HBr. And essentially what's going to happen is the hydrogen-bromine bond is going to split in half. The electron from the hydrogen is going to pair up with the unpaired electron of the oxygen, and then the other electron in the bond is going to go to the bromine. So my arrows would look like that. Now, I didn't put the transition state in for the first step. I should. The transition step for the first step is I'm breaking the oxygen-oxygen bond. In all free radical mechanisms, there are no charges. So there's not any charges in any of these reactions or in any of these steps. So what I have is, now I have basically, I'm going to form water and a Br dot once the bromine picks up its unpaired electron. Okay. So that's going to be my final product. Now this bromine really isn't a radical, it's just a bromine atom. Right? It's just a neutral bromine atom. It still would like to get to 8 electrons. But right now it's just a bromine atom. So you can call it a bromine radical, but really it's a bromine atom. As far as the transition state goes, what bond did I break? I broke the HBr bond. What bond did I make? The oxygen-hydrogen bond. So the transition state is going to look like that. Partial bond between oxygen and hydrogen, partial bond between hydrogen and bromine. Okay. So this is essentially step 2 of this mechanism. And at this point, I've done nothing with the double bond. All I've done is make a bromine atom, which is what the purpose of the hydrogen peroxide is. So now comes the third critical step. And that is that the bromine atom is going to add to the double bond. So I'm going to take my bromine atom and I'm going to rewrite the double bond over here. So it's pointed at the Br dot. And instead of writing the mechanism initially with the arrows, or writing the true mechanism here, I'm going to kind of show you what happens. So if we let's treat this carbon-carbon double bond as if it was 2 independent unpaired electrons. So that in essence, this carbon has an unpaired electron and that carbon has an unpaired electron. Now it doesn't, right? It's a carbon-carbon double bond. But what happens is bromine can choose which carbon it wants to pair up with. So for instance, it could pair up its unpaired electron with the CH2. If it does that, we're going to form the bond to the CH2, and that's going to leave the CH with its unpaired electron. The other option is for the Br atom to pair up its unpaired electron with the CH. If it does that, that's where the bond is going to form. And it's going to leave the CH2 with the unpaired electron. So this is the critical part of the mechanism. This is where I'm adding the bromine to the carbon. The question is, which carbon am I going to add to? We already know that because I told you it was going to be the one on the right. It's going to be the CH, but why? Why is this reaction going to go the way it is? So now we have to take a little bit of a digression and talk about radicals, carbon radicals. So the first thing about a carbon radical is that it has an unpaired electron. It has 7 total valence electrons that it shares. Now, we're going to always compare radicals to carbocations. But a radical, it is in far better shape than a carbocation, because a carbocation only has 6 valence electrons and a radical has 7. So it's closer to 8. What stabilized carbocations? Having alkyl groups attached to the C+. What's going to stabilize a radical? Same thing. Having an alkyl group attached to the C dot. Why? The hydrogens are all delta positive. The carbon in that alkyl group is delta minus. What can that delta minus do? It can push electron density into the C dot. And so now it's closer to 8. Same exact thing we did with the carbocation. The only difference here is that we're starting in a much better position of 7 electrons instead of 8. And what does that mean? Well, it still means that a tertiary radical is more stable than a secondary radical. But now, because the primary radical is so much closer to 8 valence electrons, there's no prohibition against writing primary radicals. They are perfectly fine. They're not stable. They're not as stable as secondaries and tertiaries, but they are stable enough to form at room temperature. Whereas primary carbocations, no, you're not allowed to draw those. You are allowed to draw primary radicals. Okay. For the same reason as a carbocation, because the more alkyl groups, the more stable the radical is. You can also have stable radicals from being next to double bonds. So for instance, when we had this primary carbocation, we said that is stable because it's what's called an allylic carbocation, because the C plus is next to the double bond. And I could move this pair of electrons so that I could form that second resonance structure. And the more resonance structures you can draw, the more stable the molecule. So having a carbocation next to a double bond in the allylic position was stable. Probably as stable as a tertiary. Same thing's true for a radical. If you had an allylic radical, you can draw its resonance structure using the half arrows by basically splitting this carbon-carbon double bond, taking one electron and pairing it up with the CH2 dot, and then giving the other unpaired electron to the other side, so that we would still be able to draw our resonance structure. And with 2 resonance structures, the molecule is more stable than it would be just as a primary radical. So the same thing that was true for carbocations is true for radicals. If you put them next to a double bond, they're going to be as stable, if not more stable, than a tertiary. Okay. And this is one of these cases where the book foreshadowed this months ago. But Just like I will give $10 to any freshman who walks in my office that has their B00 number memorized. I would give you $10 if you can remember that we actually talked about this, or that I posted it on Piazza at some point when somebody said, why does a radical have like 3 arrows and the other one, the book says it only needs 2? That was because we would get to this point, Mary.
Okay, so when we're doing this, are we supposed to be considering like which carbon to add the bromine to based on like where the radical would be and therefore like how stable that radical would be?
That's exactly our next step. That's exactly what we're going to do. Okay. So what I did was I took a little diversion here to explain why a tertiary radical is more stable than a secondary. But the big difference is now primary radicals are stable, so we can write them. And then to remind you of the fact that there is this resonance structure possible. Okay. The freshman thing with the banner ID, they've all been coming in to get permissions for various general chemistry classes, and every one of them has to pull out their phone and tell me what it is. By that time, I could have typed in their name and searched it myself. I'm sure many of you have to pull out your phone to remember what your number is too, but it's just kind of, I made them a bet, and I have yet to pay off. So, let's jump back to up here. Question would be then, I can add the bromine to carbon A, I can add the bromine to carbon B. Where am I going to add the Br dot? Am I going to add it to carbon A or am I going to add it to carbon B? Does everybody have an answer in their mind? They just don't want to say it? All right, we'll say it all together on 3. All right? 1, 2. Well, I heard a B and an A. Do we need to vote? We'll vote. Vote B or A. So where am I adding the bromine? This is a critical part. Am I adding the bromine to carbon A or carbon B? That means that if I add the bromine to carbon A, I get this product. If I add the carbon to bromine B, or bromine to carbon B, I get that product. So we want to make sure we're all voting for the same thing. Okay? So is it going to be A or B? And it's not C 50-50. It's going to be either A or it's going to be B. Okay? All right, I have a 13-13 tie between A and B. So I think we need a moment to discuss. So discuss, and then we'll re-vote and see if we can somehow break the tie.
You wrote it on the right.
Yeah, so you connect it. So if you connect it to B, if you have the bromine to B, then the radical will be on the end and do it with your primary radical.
Are we ready to vote? To re-vote? Okay, let's go ahead and re-vote. Okay. We've moved to 19 A's and 8 B's. Why A?
Because A gives a secondary carbocation, or not carbo, secondary radical.
Okay, stop there. So what kind of radical is this? It's secondary. What kind of radical is B? Primary. Which radical is more stable? Which one is more stable? Secondary. Anybody? Now I heard people say, but on the previous slide, he wrote, and I'm assuming he is me, wrote this, so that must be the answer. Which is true. Unless I'm wrong. And one of these days I will teach a class completely wrong just to see who catches me. What? No, that day somebody will be in here like observing me.
Oh.
So it won't look good, but I have tenure. What are they going to do? I did that once. I got the next semester in lab, we have upfield and downfield, and I got them completely reversed for the entire period. And then at the end, somebody goes, "Didn't you have those reversed the whole time?" And I go, "Yeah, I guess I did." Just showing you how difficult it is to try and keep those straight. Somebody was observing me that day. But no, that's what I wrote before, because I said this is anti-Markovnikov. But why is it anti-Markovnikov? Because now I'm adding something different. I'm adding a BR dot. And so when I add the BR dot, it's the same analysis that we did with the carbocation. If you remember back all the way to last week, or maybe it was the Friday before that, we added H plus to the double bond. We added H plus to one carbon, added H plus to the other carbon. What was the major product? The major product came from the most stable carbocation, which in this case would have been secondary over primary. In this case, all I'm saying is the most stable radical is going to lead to the major product. And in that case, it is going to be the secondary radical. But I've changed what I'm adding, so I'm changing this to anti-Markovnikov, because now I'm adding BR instead of H. Okay. Does that make sense to everybody? No?
I just don't get why BR changes. I don't know why it's anti-Markovnikov.
Okay. So what I did to change this reaction was I took it out of a carbocation mechanism. And the way I did that was by adding the peroxide. So when I add the peroxide, what now happens, and I should probably have a little triangle here to say heat, because it's going to require a little bit of heat for this reaction to go. But now what happens is, with the peroxide there, if one molecule of peroxide breaks apart to form these hydroxy radicals, then it's going to start a cascade of reactions that is going to be completely different. And if you're sitting there going, but wait, wouldn't the HBr with or without the peroxide immediately add to the double bond? So that it doesn't matter if the peroxide is there? Because that's a question that just popped into my mind. And sadly, I know the answer to that, because we've been trying to add HBr to a double bond in a research project. And one of the things that you find is that in the book, they never tell you how long this reaction takes. Like, we stir this reaction at room temperature for a week, and only about 50% of the HBr adds, which surprised me, because I never thought the reaction would take that long. So there's that unwritten sort of rule here, or that unwritten observation, that it's not an immediate reaction. Now, I may have said on Friday, if you added a drop of orange bromine to the liquid, it would immediately react. That's true. Bromine immediately adds to a double bond. But HBr, it takes a lot longer than you would think. So if you're going, well, but the HBr would immediately react. Actually, it doesn't. But the peroxide, all it takes is just for the peroxide to break apart. Now, all of a sudden, it grabs the hydrogen from the HBr. The Br dot now adds, and so I undergo a completely different mechanism than adding H plus. Mary?
If you go back to the other slide, so why did we write at the top, that's supposed to be the double bond, why does it only have one bond?
Because what I did was I took the second bond and I gave each carbon an unpaired electron, so it was a little bit easier right now to see that the bromine has a choice.
And is this how you would?
No, this is not how we'll write the mechanism. I'll show you how we'll write the mechanism in a minute. But I'm just trying to show you that there's a choice in the Br dot adding. Because this addition isn't quite what radicals normally do. They normally grab an atom. This is going to be an addition where the bromine's going to add to the double bond, and I'm kind of showing you how that happens. Sabrina. Yes.
But the H would add to the carbon with the most hydrogens.
That's Markovnikov.
Okay.
So Markovnikov, the H, remember Markovnikov, the H or the E plus adds to the carbon with the most hydrogens. And then the nucleophile adds to the other carbon, which is the most substituted. I guess I didn't. There's a saying with incredibly bad English about the Markovnikov's rule. Now, Markovnikov's rule only applied to H. We've expanded it to apply to E plus, bromine, mercury. But I have in the past said, them that has gets. What does that mean? The carbon with the hydrogen gets the hydrogen. In the double bond, the carbon with the hydrogen gets the hydrogen. That's another way to restate Markovnikov's rule. So the hydrogen or the E plus always adds to the carbon in the double bond with the most hydrogens. The nucleophile adds to the most substituted carbon up, and in a Markovnikov addition, we form a carbocation. The carbocation is going to be most stable when it is attached to the carbon that is most substituted. The carbon with the most hydrogens, by definition, is not the most substituted. So that's Markovnikov addition. Up here, the hydrogen added to the most substituted, the bromine added to the carbon with the most hydrogens. Anti-Markovnikov. Okay. So what happens is this, that when you add the peroxide, it completely changes the mechanism by dissociating, grabbing a hydrogen off the bromine, and now changing what is adding to the double bond. It's not an H plus anymore, it's a Br dot. And so I've completely changed the mechanism by adding peroxide. So that's why it's changed. That's why the mechanism has changed. That's why the addition has changed. Right? Everybody kind of with me? Sort of? Does it make sense? Because now what I'm going to do is I'm going to write the true second step of the mechanism without having the two dots. So if I was writing that mechanism, here's what I would write. I would have my CH2 double bonded to my CH, and I'm going to basically add the Br dot to the CH2, and then the other electron in the double bond goes to the CH. So that would be how the arrows work with the double bond. I would end up with the Br attached to the CH2 with the CH dot. What would the transition state look like? The transition state would have if I write out the molecule without the double bond, what would it have? It would have a partial bond between the carbon and the bromine, and then a partial double bond, because that's what's being broken. And that would be the transition state. Notice that there's no delta dots in this mechanism. Sometimes we do have a delta dot, but it's not in this case. All there is the bonds that are being made and broken. No charges, because there's no charges. Okay, so that's what the transition state, that's what the real second step would look like. What I showed you earlier with this one was simply, I'm trying to get and reinforce the idea that the Br dot is going to add to the carbon. Because most of the time, the Br dot, well, as we saw, most of the time radicals are actually taking atoms away from something. This is one case where it adds. And that's how it adds. Okay. So that's the second step. So what I've just written is the most stable radical of the reaction. Now in step 3, that radical, that carbon radical is now going to add to, well, it's going to react with an HBr. And what it's going to do is that carbon dot is going to go ahead and grab the hydrogen or abstract the hydrogen from HBr. So I'm going to break my HBr bond. I'm going to pair up the C dot with the H dot that results from that. And I'm going to give the Br its electron. So the arrows would look like that. The final product is going to be adding the hydrogen then to the CH, so that I added H and Br across the double bond, anti-Markovnikov. And the transition state for this reaction would be, I'm forming the bond between the carbon and the hydrogen, and I'm breaking the bond between the hydrogen and the bromine. And so that would be the transition state. So again, the transition state just is only about what bonds are being broken and made. Okay. So this mechanism is 3 steps. Breaking apart the 2 OHs, having the OH react with the HBr. Sorry, it's 4 steps. The Br dot adding to the double bond, and then the carbon radical reacting with HBr. So it's 4 steps. Is everybody okay with me?
Can you repeat that one more time, the 4 steps?
Break the hydrogen peroxide apart to form 2 OHs, 2 OH dots. Have the OH dot react with the HBr to make a Br dot. Have the Br dot add to the double bond, which is number 3. And then have the carbon C dot radical react with HBr in the final step.
So the reason it's anti-Markovnikov is because of the peroxide being there.
The peroxide changes what I'm adding to the double bond from a carbocation, or from an electrophile with a plus charge to a radical. And that changes the way the radical adds to the carbon to make the most stable radical, but the most stable radical, I added the second thing first. Right. H plus and Br minus, the Br minus would be the nucleophile. In essence, what I did was I added the nucleophile first. And that generated the most stable radical. So then the H added to this, H added second. So without peroxide, it's Markovnikov. With peroxide, it's anti-Markovnikov. Any questions? All right, now, I want to point out something about this radical reaction, and we'll see this when we come back. The problem with free radicals, number one, is they're unstable. I mean, most radicals are, chemistry and otherwise. They may be brilliant, but they're still a little unstable. Hence radical. One radical in chemistry, maybe in life, generates a whole bunch of radicals. And what do I mean by that? At the beginning, if I broke apart one hydrogen peroxide molecule, what would happen? I get two OH radicals. What do those two OH radicals do? They react with HBr. Because it's an odd number of electrons, and the number of electrons on both sides of the equation have to always be equal, you're going to end up with an odd number of electrons as a products. So one radical always generates another radical. And then what happens when that Br dot reacts? When that Br dot reacts, as it did up here, what did I end up making? Another radical. What did that radical do? It reacted with HBr. What did it generate? Well, I didn't actually put that down here, but I should have. It generated another Br dot. So the problem with radicals is every time one reacts, it generates another one. So it seems like an endless process. Of course, when does it end? It ends when you run out of stuff. You run out of double bonds. In the reactions that we'll look at when we get back, two radicals could actually come together and basically form a single bond, and that would end the radicals as well. So you hear about free radicals in, well, you talk about in biochemistry, you talk about them in things like genetics, molecular biology, you hear about them in like nutrition, right? Take this vitamin because you want to stop the free radicals. Those molecules you take are usually called antioxidants. Why do you take them? To basically keep the free radicals from running amok in your body. Where do they come from? They come from the fact that there is a resonance structure form of oxygen that looks like that. The diradical paramagnetic form of oxygen gas. So that's a diradical. We'll talk about how it reacts next semester. If I stop breathing in oxygen, I die. Right? So I got to breathe in oxygen. I don't have a choice. Some of the oxygen is going to have a free radical characteristic. And so it's going to create free radicals in my system. And hopefully there's a way to neutralize those. Because otherwise you're just going to run around grabbing hydrogens from things. You know, DNA, RNA. DNA would be particularly bad, right? Because then it would mutate. My standard line there is, you know, if it's not going to give me some sort of superpower, which right now would be laundry and dishwashing, I'll take those two. Then it's probably going to lead to a mutation that's going to be bad. So we have to keep the free radicals in check. And we'll talk about that when we get back, maybe in terms of what happens. You can't really get rid of free radicals. All you can do is make really stable ones that don't react. And that's how our body works. The antioxidants that you take all form stable free radicals that don't react, that kind of end the process. So that's the one thing about radicals. They are unstable, but in this chain process, every time one reacts, another one gets made. So it is kind of an endless process. So all it would take is just the tiniest amount of peroxide in the system, and it completely changes the mechanism of the reaction. So we have to be careful of that. Actually, saying that, I think the reaction that we're looking at as part of somebody's honors thesis, before I ever publish that, I'm going to have to prove that there's no free radical mechanism going on, because the little bit of that would change it back to what we think. So that's easier said than done. Okay, so that's anti-Markovnikov HBr addition. Goes by a different mechanism. Okay. So we have all the reactions that we're going to learn for alkenes. What would be helpful is if we had a table of all those results, except I forgot one small thing. HBr peroxide adds HBr. Anti-Markovnikov. What about stereochemistry? What if I take this double bond and I react it with HBr, H2O2, so that I add a Br dot to the double bond? So I've got my Br, I've got my CH3. Let's just say for the sake of argument that I added the Br dot from above the ring. And I now have my radical. And I'm trying to draw that p orbital so it comes towards you and away from you. So if the ring was like this, it looks like that. So maybe I added the Br up here, and the methyl group is there, and then the methyl group's coming out towards you. This is now the radical's now going to go grab a hydrogen. But my question would be, is the hydrogen going to add to the top, or is it add to the bottom, or is it going to add 50-50? So a radical looks like that. It is sp2 hybridized, and the unpaired electron is in the p orbital. So how's the hydrogen going to add to that radical? Top, bottom, 50-50. Somebody want to give me an answer? Top? I hear top. Do we all agree?
I guess it's bottom, but I have no idea why, so.
Okay, that's a guess. Sometimes guesses don't have answers. Catherine? I heard 50-50. And that's what I was going to say. With the 50-50, we have all the reasons covered. Why did you choose 50-50? Because this is similar to an SN1 reaction. The SN1 reaction being that when I had the empty p orbital for the carbocation, that the nucleophile could add 50-50, leading to 50% cis, 50% trans, overall. So you thought I didn't like that answer, right? That sounds like a good answer to me. So I have to explicitly say that in this class, radicals are going to react like carbocations in the fact that because it's sp2 hybridized, I'm going to get 50%. I'm going to get 50% addition to the top and 50% addition to the bottom. There's going to be no preference either way. Okay. You might say, what about the bromine and the methyl group? They didn't affect the carbocation. They're not going to affect the radical. So in this class, whenever we do a reaction with a radical or a carbocation, more generally with an sp2 hybridized intermediate, that carbon's always going to end up as a racemic mixture. It's always going to end up 50% cis, 50% trans. So in this case, when I add my HBr, because I'm going through a sp2 hybridized radical, I'm going to end up with 50% cis and 50% trans. So for HBr and peroxide, it's HBr, it's anti-Markovnikov, and it's 50-50 cis and trans, as far as the stereochemistry goes. Just like for any carbocation reaction. So what we really need is we need a table of reagent, what is it adding, how is it adding it, Markovnikov, anti-Markovnikov. A third column, how is it adding it, 50% cis, 50% trans. And we kind of need a fourth column that I call notes. What goes in the notes column? sp2 hybridized carbocation, sp2 hybridized radical, triangle, square, 5-membered ring. To help us explain the stereochemistry of why things are adding in the stereochemistry that they are. So that's the chart that we need to develop. Of course, it would be best if you develop that chart, because if you do it in your system, whatever your system is, and I don't mess with students' systems unless they're not going to be productive or correct. Whatever you come up with, that's going to help sync it in here. I probably have a chart that I've already written up, and I may do so, and I may put it in the folder, but if you can think about that in your own way, that's going to help you learn it in the long run. But that's what we need right now, because the next topic is regio and stereoselectivity. And let me just introduce this, and then we'll do some examples of this. Tomorrow we may end up doing them when we get back, at least if nothing else, reviewing that. So let me just talk about what goes into regioselectivity and stereoselectivity. There are two parts to each one of those terms. For regioselectivity, there's the regio part, and then there's the selectivity part. Since selectivity's in both of them, let's start with that. What does it mean to be selective? Right? If you're at the Thanksgiving Day table or whatever meal you're going to have, and you're going to be selective, what are you going to be selective about? What you decide to take, right? So number one, can you be selective if there's only one thing at the table? No. So we need more than one product to be selective. If a reaction only forms one product, it is by definition not selective. If you have more than one thing to choose from, then you can be selective and actually select one over the other. That's the other thing. You have to make a choice. If you end up with a 50-50 mixture, you weren't selective. So in these reactions, if I end up with only one product, I'm not selective. If I end up with two products, but they are 50-50, I am still not selective. So if I end up with more than one product, and one is the major product, I have now been selective. And so then the question is, what was the relationship between those two products? And that's where we get to regio and stereo selectivity. And so that's what we'll talk about tomorrow. And then continue on, or bop that up.